we're back for Unit 6, Topic 3, one of the big topics in calculus. It's part 1 of the fundamental theorem of calculus. There's actually 2 parts. This is a big moment today, right? Because we're going to be connecting derivatives and integration, derivatives and integrals. And so let's read through this theorem together. It says, suppose f is continuous on the closed interval a to b. Okay, here's some function we're going to use as our example. And big uppercase f of x equals the integral from a to x f of t dt, where this variable x is somewhere between a and b. Okay? Then the first part of the fundamental of theorem of calculus tells us that the derivative of big F is equal to the derivative of the integral, right? And that is also just equal to the function evaluated at x. So let's work through this by looking at this graph here. Let's talk through it. Where's my black pen? Okay, so let me zoom in a little bit. Okay, so here's our closed interval a to b. There's our function. The integration here, it's saying from a to some value x. So I don't know, let's just put x here. Right, so we're talking about from a to x. So if that's x, we're talking about the area under the curve here. Okay, so what is this telling us? This is telling us that the area under the curve from a to the x is equal to capital F of x. Okay, so we can represent it as that. So it's the capital F of x. It's this new function that tells us the area under the curve, which can be found using the integral. Okay? All right, that area is f of x. So we know that this integral symbol means the area under the curve. So let's just rewrite this here. Capital F of x, that green space, is equal to the area under the curve from a to x of some function f of t dt. This is hard to see, but this is y equals f of t. Okay, sure, fine. The only thing that matters is that x has to be somewhere in between a and b. Okay, now let's talk about the second part. If I take the derivative of capital F, the first part of this fundamental theorem of calculus is saying that is equal to the derivative of this integral. Okay. Cool. Well, how do you find the derivative of that integral, right? Well, how is that helpful? I don't know how to find the derivative of an integral. Well, that's what this last part is telling us. That is equal to. This is equal to that. Right? I'm just rewriting what I have. But it's also equal to that last part, which is f of x. That just means I could take this function in here and plug in an x, and I'll have the derivative of the area under the curve. Right? So what's the big deal here? Let's write it. The big deal is that if you derive the area, if you derive the function, so I'm going to say, I was like, why doesn't that make sense? The function for the area under a curve, you get the function. And why is it important? Because it connects derivatives to integration, right? Essentially, the integral and the derivative are the opposite of each other, okay? And sometimes this df dx can be written as this, right? Capital F prime of x, right? And this thing that we've set it up as big F of x is actually called an antiderivative. It's the opposite of a derivative. It's an integral, right? So if I take the derivative of this opposite of a derivative, I end up with the original function, right? They cancel each other out. So another thing you could write here is that, let me write it in a different color, is when you've been finding when you're finding the area under a curve, right? You guys can probably hear Kieran out there yelling, playing a game. He's playing Beyblades, if you guys remember those. So when you find the area under a curve, you are finding the antiderivative. You're finding the opposite of a derivative. Integrals are the opposite of derivatives. Therefore, it's called the antiderivative. So this is what this is saying is when you take the derivative of an antiderivative, you just end up with the original function, right? Because they cancel each other out. So what does that mean? Let's try this example. It's telling us to find the derivative of an integral. Okay, so if I look up here, here's my a to x, right? And then all of this is just some f of t, and there's dt. So if I'm taking the derivative of an integral, the answer is just the original function. So all I have to do is take this original function and plug in x. So the answer becomes cosine squared instead of t of x over ln of x minus delta x. That is the answer to this. Right? This a value doesn't matter. It's just a constant. Right? The original function is just dependent on the x. Okay? The derivative of an antiderivative is just the original function. Let's try some more. All right, definite versus indefinite integrals. Okay, so we've been talking about definite integrals a lot, the ones that have a specific starting point and a specific end point, like find the area under the curve from -2 to 2, right? There can also be indefinite integrals where they don't give you bounds, and you can still find the integral, or you can still integrate them. So this is like the start of this. We're going to talk about this more, right? Because what we have now is we have one bound. We know it starts at -2, but we don't know where it ends. It ends at x. So it's indefinite because we don't know what the endpoint is. So look at this function. It says g of x is equal to this integral. So g of x is equal to the area under the curve from -2 to some value. Given an x, the function g of x is the area under the curve from -2 to x, what I just said. Find g of 1 and find g of 2. So they're telling us to plug in 1 and plug in 2. Okay, so g of 1, let me switch to a darker color. G of 1 is just going to be from -2 to 1 of f of t dt. Well, what's the area under the curve from -1 to 2? Whoops, I just did that the wrong way. From -2, so I'm going to include all this, to 1. So all of this right here, right? So I'm just going to break it up into this rectangle and then this triangle here. So what's the area under the curve? Let's just count. Well, this is 1, 2, 3, 4, 5. That's 15 here, right? So it's 15 plus, what's the area of this rectangle? 1/2 times 2 times 1 is just 1. So it's 16. Right, what's g of 2? Well, it's going to be -2 to 2 of f of t dt. So it's going to be equal to 16 plus this extra little strip here, because now we're going to 2. How many is in that strip? 1, 2, 3, 4, 5. So 21. So let's use this along with the part 1 of the fundamental theorem of calculus to find some derivatives you'll see here. So here they give you g of x is equal to this integral. Now they want the derivative of g of x. Okay, so we have to take the derivative of the integral. If you take the derivative of the integral, or if you take the derivative of the integral of a function, you just get the function, right? That's what the fundamental theorem of calculus said. So to find g prime of 27, I need to take the derivative of g of x. And if I take the derivative of one side, I have to take the derivative of the other side of the equation. Right? Okay, so the derivative of g of x is just g prime of x. What's the derivative of this function that's being integrated? Well, we're using, remember, that d dx of a to x of f of t dt is just equal to f of x. That's a fundamental theorem of calculus. So all I have to do is find f of x. So g prime of x is just equal to the cube root of x. That's it. It's equal to f of x. So now I need to find g prime of 27. Well, that's a cube root of 27, which is 3. Okay, let's try another one. Here, f of x equals 2t minus 1 dt with integral from 1 to sine of x. What is f prime of x? So we have to take the derivative here. So if I'm taking the derivative of the left side, I also have to take the derivative of the right side. Okay. So what does that mean? That means that f prime of x is going to be equal to just f of x, right? But we have an issue here. This isn't an x. This is sine of x. This is a composite function. So what do we do when we have to find derivatives of composite functions, right? Remember that? We have to use chain rule, right? So the chain rule has to be used here. So if you want to, let's put a little note. A composite function must use chain rule. It didn't go away, it's still here. So remember, a composite function is like h of g of x was the notation. To find the chain rule, to find h prime of g of x, it was equal to h prime of g of x, whoops, times g prime of x. Remember that? It's a chain rule. Okay, so you basically, it's going to be equal to the original function, f of x, times the derivative of that inner function. So here we would write f prime of x equals, we're going to take this function and find the regular old f of x, but it's not x, it's sine of x, so it's 2. And so plugging in for t, I'm going to put sine x minus 1. But because we're using chain rule, we have to multiply it by the derivative of the inner function. What's the derivative of sine x? Cosine x. So that is the derivative of the integral. Try a couple more. I think this is the last page, or do we have? Yeah, it's the last one. Okay. Find the derivative of that function e of to the t plus t all square rooted from 4 to 3x squared plus 1. So again, it's not x, so I know I'm going to have to use the chain rule, right? So they want us to derive this integral. So I'm going to use my fundamental theorem of calculus, and I'm going to use the chain rule, right? So I know it's going to be equal to, if I just plug that in, e to the 3x squared plus 1 plus 3x squared plus 1 all square root. Right? That's the f of x part, but because we're using the chain rule, we have to multiply it by the derivative of this inner function. What's the derivative of 3x squared plus 1? Well, that's just 6x. Okay, and I could rearrange it and rewrite it, but I'm not going to. I'm just going to leave it like that. Let's try this one. Find the derivative of this integral. Oh, and this is, we're going to rewrite, I'll just rewrite it big over here. I wrote this as a typo. Should have been the other way around, so let me just rewrite it right here. From 5 to x cubed of t to the 4th plus 1 all to the 1/3 dt. Okay, so that's just going to be equal to my f of x. So I'm going to take this and plug it in. So it's going to be x cubed all to the 4th plus 1 all raised to the 1/3 times, because it's a composite function, times the derivative of this thing, x cubed, which is 3x squared. So So if I rewrote it to try to make it nice, I might say it's equal to x to the 12th plus 1, all raised to the 1/3 power, and I put my 3x squared up front. Okay, hopefully that's making a little bit more sense. Now see you next time.